when we're going to break down or when we are going to combine together different molecules, we need enzymes. This is how it goes. So either or, no? You know that in every reaction that we actually have in chemistry, we can produce a product, either or. We do not lose anything. In fact, enzymes cannot be destroyed. Enzymes can just actually be reactivated over and over again, but it will never be destroyed. You know that this is a principle that we know in chemistry. No, so this is one molecule of glucose 1-phosphate, right? And this is UTP, all right? Uridine triphosphate. We can actually come out with, we are going to remove 1-phosphorus by the action of pyrophosphorylase. Now we can actually produce here UDP glucose, uridine diphosphate glucose. This is actually the one that will be required, all right? So glucose 1-phosphate plus uridine triphosphate will produce uridine diphosphate glucose plus PP, all right? This is pyrophosphorylase plus water, okay? And we use a phosphate in this case. Now, the glucose 1-phosphate plus UTP plus water, we will be producing a molecule of uridine diphosphate glucose plus 2 molecules of phosphate. Now, although the reaction is reversible, as I mentioned to you, as the 2 arrows indicate, now the hydrolysis of the pyrophosphate pushes it to the right. That's actually how it goes, no? So the reaction is always reversible. You know that in chemistry, no? 1 plus 1 equals 2, 2 equals 1 plus 1. So always, no? The reactions there is actually reversible all the time, no? Moving forward, so let us try to look into glycogen synthase, the catalysis of glycogen synthase using alpha 1 for linkages, right? So this is what we know of coming from more active glucose, that is uridine diphosphate glucose, right? This is how it goes. This is uridine, a molecule of uridine, and this is actually glucose plus 2-phosphate. That's the reason why we call it diphosphate. 1, 2. And the whole molecule is uridine, and this is actually your glucose. Plus, we are going to come out with the residue that is actually glycogen. Now, we are going to build up already additional form of glycogen. No? A primer of at least 4 units that are required via glycogen. Now, the glucose is added to the non-reducing end, therefore building up additional glycogen. So we add additional glycogen residues because this one will not be useful anymore because there is excess glucose in the blood. We will therefore deposit this either in the liver or in the muscles so that we can actually annihilate an excess number of glycogen. So this will be stored in the liver and in the muscles. The UDP and UTP plus glycogen, we produce excess glycogen residues that will be deposited in 2 parts. So this is actually what I was telling you in the class all the time. Now, in excess glucose, if you're going to look at the process, it's complex, but to simplify it, excess glucose will be deposited in the liver and in the muscles. That's how it goes. Okay? Now, let us try to look into the branching enzyme that's forming alpha 1 and 6 linkages. This is remodeling, right? This glucose or this glycogen, no? The enzyme breaks the alpha 1 and 4 link. So remember, there is always a link, interconnection between 2 molecules in the alpha 1 and alpha 4. How they are connected using the phosphate content, right? So a large number of terminal residues are now available for glycogen phosphorylase degradation at the same time. Okay, this is how it goes. So the branching increases the solubility of the glycogen. So the more glycogen that you can actually produce, the easier it will be to break it down. Therefore, you need a little less of phosphorylase to break it down. and to come out with glycogen 6 phosphate. Okay, and glucose 6 phosphate. All right. So moving forward, always take note of this. Now we need glucose from glycogen in the form of glucose 6 phosphate. That's how it goes. All right. Now, so let us try to look into. Can you see the slide?
Yes,
Yes, we can.
Do you follow? Oh, a little bit difficult. By the way, I already uploaded the book. If you have time, you download the book. No, don't look at the assignment yet there. No, because the assignment is still going to be changed, and I'm going to send you also the subject matter for TBL. TBL is more on obesity, no? Because obesity is one of the big problems that we have. I'll be sending you the material so that you will actually read something about it. But if you have time, you download the textbook. I give you at least 4 textbooks there.
Please don't make the assignment 2000 today, this time, okay?
No, it will be easy. I'm thinking about it.
Yeah.
All right. Okay. So the glycogen synthase is the regulatory enzyme in the synthesis of glycogen. Take note, glycogen synthase regulates the enzymes in the synthesis of glycogen. That is, in the building up of different glucose to come out with glycogen, we need a regulator, and that regulator is called glycogen synthase. The enzyme, on the other hand, is regulated by covalent modification and phosphorylation. You know the covalent bonding, isn't it? Yeah? This is the binding of 2 elements together to form a substance. So covalent bond is a very strong bond, right? So where molecules are sharing together different, the two elements will actually share electrons, okay, complementing one another. And sometimes it's very difficult to break, no? That's why we need also an enzymes to break it down, okay? Moving forward, the regulation of glycogen synthase. When the enzyme is added with phosphorylase, or what we call as phosphorylated, this is inactivated. It does not work anymore. It will be going on a relaxed state. The active A form of inactive phosphorylated B will actually be formed from active to inactive. That is from A to B. Always take note, when we talk about enzymes, particularly in glycogen, A is active and B is inactive, right? Now, the B, phosphorylated B, will actually be activated only if phosphorus is removed, all right, so that we can actually convert the phosphorylated B to phosphorylase A. Moving forward, now notice that phosphorylation has the opposite effect of glycogen phosphorylase. Phosphorylation is addition of phosphorylase, right? Therefore, if we're going to add, there will be the activation of phosphorylase in the liver. That's how it goes, okay? So this is what we are actually looking at, no, in glycogen synthesis. Glucose 6 phosphate, you're very familiar with this. We produce glucose 1 phosphate. We remove glucose 1 phosphate. The glucose 1 phosphate plus uridine triphosphate, we produce uridine diphosphate and glucose plus phosphorylase phosphate. Then phosphorylate phosphate plus water, we produce 2 phosphate. Then
Doctor,
UDP,
excuse me.
yes.
The slides are stuck.
Oh, all right. I think you better you can see now. So you are familiar with this. Now this is the byproduct, the glucose 6 phosphate. Again, if we're going to synthesize glycogen, similar way, the glucose 6 phosphate will actually be converted into glucose 1 phosphate. The glucose 1 phosphate will be added by another molecule called uridine triphosphate, so that will come out with uridine diphosphate and glucose plus phosphorylase phosphate. The phosphorylase phosphate that is inactivated with water, all right, we will produce 2-phosphate inactivated. UDP glucose plus glycogen, therefore there is already the UDP glucose production plus glycogen. Now the glycogen, there is excess, this is what we call as residue, right? So this is how it actually goes, no? The UDP, then there is the production of ATP, right? We use ATP, therefore we will produce uridine triphosphate plus adenosine diphosphate. Always take note of this. During this reaction, that will be the time that we can actually produce energy source. Always take note that the reaction happens so quickly. Just that I'm showing you how it goes. Now looking forward, the glucose 6-phosphate plus adenosine triphosphate plus glycogen plus water, the reaction will be the production of glycogen residue that will be deposited in the liver or in the muscle plus adenosine diphosphate plus 2-phosphate. Only one ATP is used to store one glucose residue in glycogen. Always take note of this. Only one ATP, right? That is actually used. That's why we need a lot of ATP. But during this process, we only require a minimal amount of ATP in order to store one glucose molecule residue excess in the bloodstream in the form of glycogen. This is how we are going to synthesize glycogen from excess glucose. I would like to make it clear, no? If you have a lot of glucose in the blood, it will actually undergo this process, the glycogen synthesis. All right? That's how it goes. Okay. So this is how we are actually looking into, no? The glycogen synthesis and breakdown are reciprocally regulated. We build glycogen, we break down glycogen. These are also regulated. You know, we need to regulate this also at the same time, because overproduction and overbreakdown will result into problems in the body. There will be what we call as metabolic problem. You see, and a lot of people do have disease like that. Most of the time, if we have problem like this, we could have obesity, we could have problems of the liver, we could have diabetes, we could have so many sort of problems, systemic problems that we know of. Okay? All right. So now let us try to look into protein phosphatase 1. The protein phosphatase 1 dephosphorylates phosphorylase kinase, and phosphorylase A. Remember, this is the active form of phosphorylase, thus inactivating glycogenolysis. The protein phosphatase will always be the one to regulate the glycogenolysis. What do you mean by glycogenolysis? The breakdown of glycogen. Always take note of this. Now I'm going to give you a secret in understanding scientific terms. Glycogen, lysis. And you know this already. Lysis is breakdown. When you say glycogenolysis, the breakdown of glycogen, right? So that will be regulated also by protein phosphate. We will not be producing. Imagine this, no? Can you imagine without the action of protein phosphate, what happens that you keep on eating a lot of carbohydrates, let's say a lot of biryani. Therefore, a lot of sugar will enter in your bloodstream. And what happens that if glycogenolysis will not be regulated is that the liver will keep on producing also glucose 6-phosphate. So sugar will be concentrated in the bloodstream, leading to hyperglycemia. But eventually, you're going to toil your pancreas. What happens is that there will be a very big problem already. Either you could actually destroy the pancreas, because, you know, pancreas is the one that actually produces insulin. You know, insulin is the one that is breaking down sugar, isn't it? So what happens is that you could actually have some sort of pancreatitis or any other form of pancreas breakdown. you may be having long-term effect on that, maybe diabetes, or maybe dead. You will be dead, you know. So this will be the problem. That's the reason why we need to regulate all the molecules that come in and that come out inside the cell. And this will be regulated by different enzymes, particularly in the liver. For glycogen, it will be regulated by protein phosphatase. Now, the protein phosphatase 1 also dephosphorylates glycogen synthesis B, thus activating glycogen synthesis two ways. This one inactivate, this one activates. Either or. Okay? It activates a glycogenolysis, or it activates also a glycogen synthesis. See? That is how your protein phosphate work. Right? So moving forward, this is how it looks like. No? The protein phosphate 1, the phosphorylase kinase, and phosphorylase A, thus activating glycogenolysis. This is how actually it works. No? How we activate your glycogenolysis, as I already mentioned a while ago. From phosphorylase B to phosphorylase A. You know, the glycogen is actually reacting to epinephrine. All the muscles will be acting to it, will be actually acted by epinephrine. It will react to epinephrine. Epinephrine is a form of hormone, and epinephrine is a form of protein also. So it will undergo this process as discussed to you earlier. Now, protein kinase A to protein kinase A, then it will be producing glycogenolysis, right? All right. So we can actually see the inactive state to be converted into active state. Therefore, phosphorylase A will be the one that will produce sugar from glycogen. That's how it goes. All right. This is actually the opposite also. So this is the glycogenolysis. This is also the reaction showing the synthesis. Remember the main difference. Remember here, the phosphorylase B will be activated to phosphorylase A. Now, the phosphorylase A will be deactivated. Okay? So it will actually come out with glycogen synthesis B. This is in active state. All right? Now, moving forward, when blood glucose levels are high, as I mentioned to you earlier, no, just because you have maybe this morning you could have taken lots of soda, you know, Coca-Cola, right, or coffee with sugar, insulin activates protein phosphatase 1, which stimulates glycogen synthesis. You see what happens that when the blood actually, when the cell detects that there is too much sugar in the blood, in the bloodstream, the protein phosphatase 1 will be activated, so that it will actually activate glycogen synthesis. No, so we will deposit excess sugar to the liver and to the muscles. And this is accomplished through a complex, highly regulated signal transduction pathway. It's very complex, no? That I will show you later on. But that's how it goes. I will show you a complete picture in a layman's term, no? When we eat something, we are going to accumulate so much sugar in the bloodstream. So it will be activated, the protein phosphatase 1 will be activated, so that we can actually convert this excess sugar into glycogen. We call that as glycogen synthesis. Now, let's see the opposite. You have not eaten for 3 days. Therefore, the level of glucose in the blood goes down. We also need the protein phosphate 1 to activate glycogenolysis. Take note of that, no? So that the glycogen from the liver and the muscles will be producing glucose 6-phosphate using the process called glycogenolysis. We need to break down the glycogen to produce the required glucose requirement of the cells. Now, always remember that glycogen metabolism in liver always regulate the blood glucose levels, not the muscle glycogen. Okay? The glycogen metabolism in the liver, not in the muscles, will always regulate the blood glucose levels. That is how it's supposed to be going. All right? So let's try to move forward. Now, the blood glucose all right. Now, this is how it goes, no? So this is how regulation that we can actually see in our liver, no? So there is increased enzymatic activity. Let's say if glucose is added, therefore we need the protein phosphatase 1 in order to synthesize. But when glucose is actually decreased, we need protein phosphate 1 to actually metabolize glycogen from the liver. That's how it goes. The inactivation of phosphorylase and an activation of glycogen actually synthase can be shown in this diagram. All right? Now, always take note, the PP1, the propane phosphate 1 here acts as a catalyst. Remember what is a catalyst, right? You have known that, no? You have known that in your earlier class or in chemistry class. A catalyst is any substance that hastens the reaction of a substance or another substance. And most of the time, the catalysts that we have in the body are in the form of enzymes. No? So besides insulin, glucose itself binds to an enzyme called phosphorylase A. Now, propyl phosphorylase 1 acts as a catalyst only when phosphorylase A is in the T state, active state. No? The conversion of active to inactive state, that is from A to B, releases PP1 to activate glycogen synthase. So this is how it goes. Glucose, right? This is how we look at it, no? PP1, the glycogen phosphorylase A, this is active in our state. When blood glucose is high, what happens is that there is inhibition. So the glycogen phosphorylase actually A will be activated, PP1. We need to convert that or deactivate that so that we can come out with glycogen phosphorylase B, that is inactivated. All right. So much glucose we need to inactivate so that we will stop the production of glucose from glycogen. That's how it goes. Now, on the other hand, the muscle phosphorylase A is unaffected by glucose. That's the reason why the main regulatory part of the sugar in the body, the level of sugar will be the liver, just because of its function, that is to store and to provide sugar whenever it's needed. So what about the insulin? Insulin is the one that is actually needed in order to break down glucose in order to come out or produce ATP. But the real regulator will be the liver. In fact, liver is actually very important. If there is a problem with the liver, then there will be a very big problem. You will be in trouble. Okay? So take note, no, that glucagon, this is actually starter states, stimulates glycogen breakdown. Because, glucagon, once that there will be insufficient amount of sugar in the blood, glucagon would actually be released. No? So it will actually assume that there will be absence of sugar or low level of sugar in the blood. Therefore, the glucagon will stimulate glycogen breakdown so that we will have enough glucose in the bloodstream. That also will inhibit glycogen synthesis. When there is glucagon, enough glucagon, always take note of this, no? The pancreas produces two types of hormones, insulin and glucagon, right? Now, when there is insulin, that means to say it's actually healthy, trying to break down sugar. But when there is already the production of glucagon, excess glucagon, therefore, it actually notifies the liver because the sugar level of your blood is less, thus leading the liver to produce the needed sugar. If it leads the production of needed sugar from the liver, therefore it inhibits also its function to synthesize glycogen. That's how it goes. Now, on the other hand, the high blood glucose level, we call that as hyperglycemia. Or let's say there is sufficient enough amount of blood in amount of sugar in the blood. This is what we call as the feed state. The insulin stimulates glycogen synthesis. Okay, less glucagon, insulin acts upon. Therefore, it will stimulate the liver in order to mobilize its enzyme to store the glucose, that is glycogen synthesis, and inhibits glycogen breakdowns. It's the opposite, okay? Always take note, no? So that's how system works. If one system will become dysfunctional in the body, then there will be a very big problem, will be trouble. If pancreas is dysfunctional, then we will be in trouble. If liver is dysfunctional, then you will also be in trouble. Right? So you better take care of your body. That's the reason why most of the time a lot of the causes of death in the world would always be considered as some sort of, let's say, multiple organ failure. One organ fails, the other organ will be affected. Just like what happens when we are going to do glycogen synthesis and glycogenolysis, right? So this will be acted upon by liver and the pancreas at the same time. So any question about glycogen synthesis? All right, now let's go to calcium metabolism. Are you familiar? Where do you find calcium in the body, class?
What is the question?
Where do you find most of the calcium in the body?
Yeah, in the bones. As
Bones.
melatonin and as I know, yeah.
So this is all right. This is actually needed. So a lot of you are actually taking calcium supplements now, especially in some of you do have problems with the bones. No, you can easily fracture the bones, among others. Right. So let us try to understand how we actually use calcium in the body, the calcium metabolism. All right. Now, the calcium is located inside the bones. This is an intra-osseous cation. The calcium is an element, right? What is that? Oh, okay. Iman is here already? Okay, can you give how many? I want to. This will be. Sorry. Okay, Delta, give me calcium. Give me sugar, chocolate. All right, moving forward now. Calcium is an intraosseous cation that is around 99% of the bones. No, the extra-osseous fraction is only around 1%. So take note of that. These are actually moving in and out of your bones, No, what do you call the cell that comprise our bones?
The bone marrow?
Osteocytes. Yeah? Osteocytes. Yeah? Okay. So we are now going to osteocytes. The first one, we actually look into hepatocytes, no? The liver, no? Now here we are going to have osteocytes. We have so much. When you say intraosseous, we are actually finding so much of calcium inside the osteocytes. 1% only is outside the osteocytes. The level is essential for normal body function because of the effects of neuromuscular excitability and cardiac muscles, right? So these are actually very important. Now, these are some of the conditions that you may encounter when there will be a problem on calcium metabolism. Hypercalcemia, for instance. Now, when you say hypercalcemia, what do we have?
High amount of sugar in your blood. Sorry, high amount of calcium in your blood.
Yes, high amount of calcium in your blood. So you can actually discover this when there is muscular hypotonia. You know, your muscles cannot actually contract, leading into cramps. Some of you do have some muscle cramps, no? Once in a while when you do exercise. There could also be cardiac arrest, and there could also be arrhythmias, no? That will be excess amount of calcium in the blood. Hypocalcemia, on the other hand, is a notable low amount of calcium, right, in the blood. So this calcium will actually be moving towards your bones, no? So in that case, there will be what we call as tetany and arrhythmias, no? These are some of the conditions that could be reflecting the level of calciums that can be found inside the body. All right. So let's see the factors affecting calcium intake and of loss, no? Intake. So the amount of calcium in the diet, of course, no? You know for a fact that calcium can be found in the diet, no? Some of them can be found in bananas, all right? And other than that, of course, the intake of vitamin D. Now, most of the people, especially those who are getting old, do have some problems with vitamin D, leading to the bone problems, you know, like me. I am taking vitamin D. Why? Because I have some bone problems, spondylosis here, no? Because I stay so much in the computer, so there is softening on my bones. There is less calcium and less vitamin D. I need vitamin D to metabolize calcium in that matter. No? On the other hand, loss. No? So the amount of calcium reaching the glomeruli. So you are actually, let's say, moving out. Yeah, lots of calcium. How do we do that? Because you take a lot of diuretics, a lot of water, excessive urination. You may remove excess, or you may remove certain amount of calciums in the body. No, and also GFR, that is glomerular filtration rate, is actually higher, and of course the renal tubular functions, the CRF, and there is actually the impaired activation of the vitamin D. There is one problem. Could kidney disease, no? Could be a problem. And then PTH, pituitary hormones, and vitamin D, no? In that matter. Then the amount of oxalate, phosphate, and fatty acid in the diet from insoluble complexes with calcium. Okay? We should know that. That's why sometimes we need to eat a lot of calcium-rich foods, like livers also. All right. So what do we know so far? Let's try to look into the concepts of plasma calcium and albumin. All right. So in this case, the plasma calcium, that is actually the calcium that is present in the blood. Sometimes we have to take this when there will be a problem with our bones. We have to look into the amount of calcium that could be present in the blood. No. So the blood contains, for a fact that the blood contains plasma. This is the fluid component of your blood that contains most of the electrolytes. No? So plasma calcium level is around 2.15 to 2.55 millimoles, no, per liter. All right. And this can be found in two forms: less than 1/2, that is bound to albumin, that is inactive, and most of the rest is actually free, that is free floating in the calcium, in the plasma, that can go everywhere, particularly in your bones, right? That is the ionized calcium. That is a charged calcium, calcium plus, right? Now the total plasma calcium is lower in the supine than in the upright position. You know why? No, if you're going to take, that's the reason why when you're going to take a sample of the blood, always take note, no? Do not take, particularly if you're taking a sample of blood with those who do have problems with bones, we need to look into the calcium content. No, when you are going to withdraw the blood, the person must be on upright position, sitting down, not lying down. Because if the person is actually lying down, so basically the plasma calcium is lower, right? So there will be inaccurate reading in that matter. All right, moving forward. Okay, blood for calcium determination should be taken without tourniquet. Take note, no, to avoid stasis. You know that, no? It leads to false increased plasma calcium. When there will be stasis, when you're going to place tourniquet, if there will be stasis, so what happens that calcium will actually flood in. So when you're going to withdraw the blood, there will be increased calcium, and that will not be good also for reading. It will provide you false reading on calcium content. There should be no tourniquet. Now, the plasma corrected calcium in millimoles per liter equals the plasma measured calcium plus 40 plasma albumin, that is in grams per liter, will actually be multiplied by 0.2, so we can come out with the following, right? We can come out with the normal reading of your calcium content. Calcium is needed, no? Now let us try to look into the relationship between hydrogen and calcium ion. In acidosis, there are different types of acidosis, right? Respiratory acidosis and metabolic acidosis, isn't it? In that case, these are two different things, no? All right, in respiratory acidosis, this is acidosis caused by excessive amount of carbon dioxide that is actually coming in. So metabolic acidosis is excessive amount of carbonic acid that could be present in the bloodstream, no? So in acidosis, hydrogen ion competes with calcium to bind protein, all right? So hydrogen and calcium are competing. These are cations, negative, as well as the increase of the solubility of calcium substances in bone, so that a free fraction elevates and may cause one condition called osteomalacia, the softening of the bones. No? Now, in alkalosis, on the other hand, the protein-bound fraction increase and the solubility of calcium substances is actually very low. So the free fraction decreases and will lead to tetany. All right, lockjaw, as we know. Okay. Now, how do we control the plasma calcium, the calcium that is present in the blood? It depends on the following: an adequate supply of calcium and vitamin D. Vitamin D is needed in the metabolism of calcium, right? So the normal function of the intestines, and at the same time, it depends on our parathyroid glands and also on how we are actually releasing that in the kidney. Can you give me 2 minutes, please? I need to finish this, right? Now, the role of PTH, calcitonin, and vitamin D in calcium metabolism. Now, the PTH stimulates the osteoclastic bone resorption, right? Okay, so increase the plasma calcium and phosphate levels. It decreases renal tubular reabsorption to phosphate and increases the calcium reabsorptions. Basically, it's just like that, no? So calcitonin, on the other hand, is secreted from C cell of the thyroid gland, decreases osteoclastic activity, that is opposite to PTH action. Moreover, plasma calcium that's located in the blood may be buried in the form of, in your in the case of medullary carcinoma of the thyroid. On the other hand, vitamin D increased calcium resorption in the intestines. In conjunction with PTH, it stimulates the osteoclastic activity. Okay? So the hyperglycemia, that is excessive amount of calcium, what happens that there will be clinical effects on an increased calcium level that could be brought about by malignancy and drugs like thiazides, right? And for some PTH abnormalities, we have the following conditions like primary hyperparathyroidism, tertiary hyperparathyroidism, and lithium-induced hyperparathyroidism. And also there is high bone turnover and thyrotoxicosis also. And there is also what we call as high level of vitamin D, among others, that could be caused. On the other hand, hypoglycemia can be caused by drugs, no? Like furosemide. Furosemide is diuretic, no? So you eliminate so much of your calcium from your kidneys, no? Causes of hypocalcemia could be hypophosphatemia, like in vitamin D deficiency, and of course, malabsorptions and kidney diseases, like in the case of CRF problem. There is other condition in the form of osteoporosis when we lack calcium in the blood, in the bones. And also there is what we call as target disease of the bones, when there is increased bone turnover and remodeling due to the increased osteoclastic and osteoclastic function. Yeah, so that actually ends our glycogen and calcium metabolism. So next week we have to look into another lesson that is on the biochemistry of the liver. We are going to look into the liver. Please download your lecture. It's already there in the website, and read something about your liver. Okay? There will be a quiz on Wednesday next week. The coverage of the quiz will be glycogen metabolism and calcium metabolism. All right? For your attendance, please write present in the message board. Okay? Thank you so much and have a good day.